Okay, this is lesson 8, and we're going to be looking at alternating current and the oscilloscope. So if you haven't got your oscilloscope out of its box, you might go do that and set it up beside the circuit board. In the oscilloscope box, or along with it, there was a little baggie that had some resistors and capacitor and an inductor in it. And as we go through this, I'll tell you what you need to use. Okay, but before we start actually using the oscilloscope, we want to look at the concept of alternating current. And we've seen before that current was direct. So in the first unit, all of those labs, the current was one direction, and that was called direct current, or DC. But it turns out that most of the current that we actually use, like if you have a plug-in, you plug in something into the wall, that current is not DC, it is AC, it's alternating. So we have the voltage as a function of time, is some maximum value times the sine of omega t. So this is just a general sine wave, and then we need to define a couple more things. Omega is 2 pi times frequency f, and we know that frequency also is 1 over the period. And the period of a wave we're going to call capital T. So we have some definitions here. And what would seem logical is if the voltage across a resistor is alternating or varying as a sine function, then the current should do the same thing. So the current as a function of time should be I max times sine of omega t. And we know from Ohm's law that V equals IR. R is the resistance, R is constant. So whatever the voltage is doing, the current should be doing the same thing. Now, we're going to look at a sine wave quite a bit, but we're also going to look at a couple of other varying waves. And so on page 63, I have a blank there so you can sketch in these wave patterns. So a sine wave is just kind of what you would expect to have. So this is sine. Now we also can have a square wave. So we have, it goes straight over and down and over and up and over and down. Let's see, I wanted to try to make 2 periods. We'll look at period in just a minute. And then we have a thing called a triangular wave. Actually, I think I'm going to do the triangular wave down here. So it starts here and goes straight up and down at an angle and up and then down. And so this is 2 complete cycles. Let's see, this is square. This is triangular. And then we have what is called a sawtooth. Now, you might think a sawtooth is going to look sort of like a triangular, and it kind of does, but it's not quite the same. A sawtooth goes up at an angle, but then straight down. And if you have looked at saws, most of the time, I think, it looks more like this than the triangular wave. So we go up like this, straight down, and then like so. So this is sawtooth. Now we aren't going to do anything with the sawtooth wave. I just wanted to mention that because it is one that can be used. But in our circuit board and the oscilloscope, circuit board does not have a way of producing a sawtooth, but it does have a way of producing these other three waves. Now, something that you may or may not know, and it's not really necessary, but I thought I would just tell you anyway. The general way that these square waves and triangular waves and actually any kind of wave is constructed is with a combination of sine waves. And so there's a thing called Fourier series and Fourier analysis and a lot of mathematical things like that. But the idea is that if you combine the proper sine waves that have the proper amplitude here and a coefficient here, that you can actually construct a square wave or a triangular wave or a sawtooth wave. So that's basically how the function generator in the circuit board produces these various waves, is by having the proper combination of sine waves so that when they're added together that they get what we want. Now, a couple of other things that we're going to need to keep track of is amplitude. Now, the definition of amplitude is from the horizontal axis to the maximum. So the amplitude is from this axis up to here. And what I'm going to call that is the voltage and a subscript P for peak. So here we would have, this one is V of the peak. Now we also sometimes talk about peak to peak voltage. And so that's from the very top to the very bottom, or very top to the very bottom. Once in a while we talk about that because if we're looking at the oscilloscope we will actually see that. But in most of the calculations, we want just the amplitude of the wave, which I subscript with a single peak. The other thing that we need is the period of the wave. And the period is the time for one complete oscillation. So on a square wave, we have, I call it a bump and a dip. So from here over to here is the period. We're going to call that capital T. And also on the sine wave, we can go from here over to here. So that time is one period. When we're actually measuring on the oscilloscope, it's going to be easier if we measure from peak to peak horizontally. So if we look at the time there, we also get the period. Now we're going to have to watch or kind of keep track of what you're measuring, because when you look at this, you see centimeters, you see a distance. But on the oscilloscope, we're going to see that the distance represents either voltage or time. And the two that we're going to use quite a bit is the vertical. So I'm going to try to color code this. So vertical, there's a knob, and we'll show you that when we get to the actually looking at the oscilloscope. But if you want voltage, the actual voltage is going to be the number of centimeters. So there's sort of a graph on the screen, and if you multiply that number of centimeters times the number of volts per centimeter. So this is on a dial, and it has various numbers, usually like 1 or 2 or maybe 0.5, 0.2. So you just notice what dial this is set on, and then that times the number of centimeters on the screen will actually give you the voltage. And you can see centimeters cancels with centimeters, so your units then work out. Now, we have the same thing for time, except time is on the horizontal scale. So we have horizontal. And the time, I'm going to go ahead and put period, because usually you're going to be measuring from peak to peak horizontally, or like from here to here horizontally, to figure out what the period is. So for the time, which would be the period, again, it's the number of centimeters multiplied by the number of seconds per centimeter. Now, you're going to have to watch, because on this dial, this is also a dial, you have to watch what it says around the out edge of the dial, because this is usually not just seconds. Most of the time it's either milliseconds or microseconds. So you have to keep track, if you're doing some calculations, you have to keep track of milli, which is 10 to the minus 3, and then of course micro is 10 to the minus 6. Okay, so there are a couple of calculations a little bit later, and I don't think I'm really going to say much about those because it explains those in the lab. And actually in this lab I seem to have a lot more instructions than I did in some of the others. So what we're going to do now is look at the oscilloscope and the circuit board. And I'm going to keep talking, and Adrian's going to refocus the camera so that we have the circuit board and the oscilloscope in it and zoomed up where you can see closely. Okay. Now, on page 64, we start with, I assume you have taken the oscilloscope out of the box. There's a power cord, and I'm not going to show you that, but it's plugged into the back. And here is the on button, so we're going to push that. And it's going to come on. We have a green line here. And I don't think I'm going to follow exactly what I have here because I've already done this, but you should do that on all of the settings there. Now, let's see. Where I'm actually going to start is, okay. Well, our other oscilloscope decided it didn't want to work anymore, so I had another one, so we now have another oscilloscope that does seem to be working properly. And the other one was working earlier, but I don't know. So if yours happens to not work right, let me know and we'll figure out what to do from there. But on this, about in the middle of page 64, we're going to connect, and I said this before, but I'll say it again. We have the probe, and when you put it on here, you have to hold on to the part that's rigid and then push and turn it till it clicks. If anything's loose, then it's not connected correctly. So we have a ground. This is what we're going to call the probe ground. We have the probe hook, and so you pull this back. I'm not sure where you can see that easily, but you pull this back and there's a little hook. It hooks onto something and then you turn loose and it stays hooked onto it. So there's a little tab in the lower left-hand corner of the front of the oscilloscope that if you look closely on there, it says 1 kilohertz and it says 2 volts peak to peak. So I'm going to connect this to here. And at the moment I don't need to put the ground on anything. I will later, but I don't right now. So if you notice here on the dial, this is one of the dials I was talking about. It's volts per division, and each division is a centimeter. I have it set on 1. So, use my pencil for a pointer. If we look here, you can see that the bottom of this is about 1 centimeter below the horizontal axis, and the other is about 1 centimeter above. So this would be 2 volts peak to peak, or 1 volt as just V sub P. Now, there are a lot of knobs over here that you can turn and do various things. One thing is this sweep variable should be to the right, fully clockwise. I don't think it doesn't seem to click, but it should be fully clockwise. And then this middle gray knob also should be fully clockwise, and it does click. So those have to do with changing or making the scale different than what the dial says, and I don't think we ever want to do that. So we notice here that our wave isn't sitting exactly on some of the lines, so I'm going to use this knob, and notice here this is in the vertical region and the little arrows point up and down, so this moves it up and down. So I'm going to get it where the bright lines are exactly on 2 of the black lines of the screen. Then it's a little bit off of the vertical line. So this position up here, this knob, notice the arrows are left and right, so it'll move it sideways. So I'm going to position it very carefully so that the left edge of this square wave is along a line, and it's very faint, so you really can't see that part of the wave. But if we count a bottom and a top, so we count here 1, 2, 3, 4, 5. We have 5 centimeters, 5 centimeters, and then if we notice on our time per division dial, it is setting on 0.2, and then over here we have ms for milliseconds. So if we have 5 centimeters times 0.2 milliseconds, we end up with 1 millisecond, and that's the time, which is the period. Then we know that our equation, what frequency, is 1 over the period. So if we have 1 divided by 1 millisecond, we end up with 1 kilo cycles per second, and a cycle per second is hertz. So this is 1 kilohertz, which is what it says down here by this little tab. So this tab is just for you to see if the screen and the probe and all of the workings are calibrated properly, and this one seems to be. So now we're going to look at a little more. This is part 3, observing signals from the function generator. So now we need to look over here at our circuit board, and we need to turn it on. And we're focusing, you're only going to be able to see this left part, because the right part we're not going to use at the moment. Up here in the top left corner, and Adrian can't, I'm not going to have him take the camera off and look straight down, but you can look up here. This top dial can be moved from 1, 10, 100, 1K, 10K, and 100K. So this is the frequency, the major divisions. So I have it set on 1K, which is what we're going to use in a little bit. 1K is 1 kilohertz. Now, on this second one here on the left, it also says frequency, but it has on the left is 0.1 and around to the right is 1. So this knob is a continuous moving knob. This one up here at the top, it sits at a particular position. So it's not a continuous moving knob. Now if you think about it, if this continuous moving frequency knob is all the way clockwise to the 1, then it means the frequency is what the top knob is set at. So it's set at 1K, 1 kilohertz. So if this is here, this will be producing a wave with a frequency of 1 kilohertz. Now, if we notice the knob that goes to various positions, if we move it one to the left, it's at 100. So the question is, what do we do if we want a frequency between 100 and 1,000 and there's no position there? So we set this back at 1,000, which is 1 kilohertz. Then we can turn our continuous moving knob down, which is counterclockwise. As we turn it down, then the frequency that it's producing is getting less. And if we turn it all the way down to here, which is 1/10, then if you think of 1/10 of 1,000 is 100. So we can change from 1,000 down to 100 with this top one set at 1,000, and then this one we can vary. Now we're going to see a little bit later, how do we figure out what the frequency actually is? And there's a couple of ways. I'm going to show you the more complicated way first, because most or part of the time you may not have a meter handy that will actually measure frequency. It turns out that one of ours does, but you need to be able to look at the screen and figure out how, things from the screen so that you can get the frequency that you want. Okay, then over here to the right of the continuous frequency knob or dial is another one. It goes from 1 up to 10, and those are sort of arbitrary numbers. It's labeled AMP for amplitude. It changes the voltage, so you can get various voltages if you want a large voltage or a smaller voltage. And then that in combination with our volts per division, you can produce the voltage that you want. Okay, then the bottom of these four is just called function generator. And if you look at the top, which is kind of down inside there, there are 3 pictures. One of them is a sine wave, which I had shown you before. The middle one is a triangular wave, and the right one is a square wave. So that's why we're going to look at those 3. We're not going to look at the sawtooth because our function generator doesn't produce a sawtooth wave. So we have to keep track of all of those dials. The other thing we need to know something about is down here in the lower left-hand corner of the circuit board, there's a little silver thing, and then there are 3 parallel lines that sort of form a triangle. This is the standard symbol for ground. Now, we do have an alternating circuit, but there still is ground. And this may be a little bit confusing, but the main thing we're going to keep track of is that ground for the oscilloscope and ground for the circuit board has to be the same place. And that's why we're going to have to make sure that we connect things properly and make measurements when things are in the proper place. And I will explain that as we go along. Okay, so now we want to look on page 65, and I'm not going to go through the step number 4 in detail. I'll just show you what it is. And I've already talked about number 2 and number 3 up at the top. So number 4, we want to build a circuit to determine the frequency of a wave. Okay? So this says to locate the ground in the lower left-hand corner here. You're going to need 2 wires, I don't know, a few inches long, and then you need not at the moment, but you will need the 5.1 kilo ohm resistor, which is green, brown, red. So I already have that. I'll just put it over there for the moment. Okay, so I can undo this. Don't need this on here anymore. And what I want to do now is to be able to get a signal that the function generator is producing and have it show up on our oscilloscope. so these wires don't always cooperate. Okay, so what we're going to do is we need to go from ground, and if you notice here, there's a white line from the outside over to several of these rows. There's a small circle here, and this goes to the inside. We want to go to the outside, so we're going to just put one of our stripped wires into any of these. Let's see, there's actually 4 rows there. You can put it into any hole in any of those 4 rows. Then we're going to just put it over here on the circuit board any place that we want. We'll have to kind of put it a particular place a little bit later, but right now we can just put it there. And then we need to get our signal from the function generator up here. And if you notice right below the word function generator knob, there are several columns here. There are 2 of them that say TTL. That's actually transistor to transistor logic, which we're not using now. So we're going to just put this into someplace kind of over here on the right hand part of this and put it in, and then it just says to put it into the circuit board a few rows from this previous black one. So I'm just going to put it there. Now then we need to connect our probe. So we have our ground of our probe, and it always gets connected to the ground of the circuit board. That's no matter what. So you need to make sure that there's enough of the black wire that's stripped that you can actually connect to the wire part. And I could connect it up here, but I want to get in the habit of connecting it down here. We just need to make sure that we connect to ground. So then we're going to connect our hook part up here to the red. Now we could have connected here, but I just decided I wanted to connect there. Notice we have a really tall wave here. So I can do a couple of things. I could change this to 2 volts per centimeter. I'm going to leave it at 1, and then I'm going to turn our amplitude down. Notice as I turn it down, the wave gets shorter. It's really spread out a lot. I would like for it to see more wiggles there. So I'm going to move, wrong direction. Change our time, and actually I'll change it to there. I'll change it to 1 millisecond per division. Okay? So what have I got up here? I have my frequency on 1 kilohertz. I have my continuous frequency dial about in the middle, so that's probably around 500 hertz. Now, we can move this position back and forth. We can also move this wave up and down. And you can change the knobs over there to get what you want. And what I have here, I said so that the wave is about 4 centimeters tall. So 1, 2, 3, it's not quite 4, so I'm going to make it a little bit more. You notice that it went up a little and down a little, so then we have to change this position. And you're going to spend a fair amount of your time moving these things back and forth and up and down to get them where you want. So right now I have almost 2 divisions. So 2 times 1 is 2 milliseconds. And if I can do this in my head, 1 divided by 2 milliseconds probably turns out to be about 500. And with this continuous dial about in the middle, and this one up here on 1 kilohertz, then that's reasonable. It should be around 500 hertz. So at this point, you're going to do several things, and it tells you in here, just follow the instructions. The next thing is you're going to use a triangular wave. So we'll go here and change this to triangular wave. Notice it's very nice triangular wave. One of the things is it looks just a tiny bit taller, so if I wanted it the same height, I might turn this amplitude down just a little bit. And then I'm going to change it on over to the square wave. So we have a square wave, and I might need to change it back up a little bit. I can also move this up and down to get it where those are on the lines on the oscilloscope screen. So that should take you through page 66. Now we're going to look at RMS values, and something that I didn't say a while ago when I was at the board. The values that we want, the voltage values oscillate, or they vary. And even if we had a meter that could keep track of those, we can't read those numbers as fast as they're changing. And even if we could, that really doesn't tell us much. What we need is some number that is characteristic of a particular wave. And the first thing we might do is think of is an average, but if you look back at the sine wave, there's as much above the horizontal axis as below. So the average is 0. In fact, it's 0 for all the types of waves that we looked at, and obviously that's not helpful. So what is helpful is what's called RMS, the square root of the mean of the square. And that is described back on the first page, so you might want to go back and read a little bit about that. But what we're going to do now is to measure some of these values and see what they are and what they are for the different kinds of waves. So we're going to start with a 5.1 kilo ohm resistor, green, brown, red. And what I'm going to do is to connect it. I'm going to put one end in the same row as the ground wire, and the other end in the same row as the wire that goes to the function generator. Okay. Now, I can't emphasize enough that when you're connecting these things, check to make sure that things are in the row that you think they're supposed to be in. So if something doesn't work right, check that first. Also check to see that your circuit board is turned on. And the reason I say that is from experience. After spending several minutes trying to figure out why something didn't work, I realized one time that the circuit board was not on, and another time that I did not have things in the same row that were supposed to be in the same row. Okay, so now what we're going to do, we're on page 67. We're going to go back to the sine wave, and we're going to measure voltages. So we can measure voltage across the resistor based on how many centimeters we have and what time we have here, or what voltage, what scale we have here. And I think on this I have you to do 2 volts. Okay, so if this is on the 1, then we need 2 volts up above the horizontal axis and 2 below. Let's see if I can get this positioned correctly. Okay, that's about right. And then we're going to look at different frequencies. So on page 67 we have a table of frequencies, and for this you're going to need to figure out how to get that frequency. So I will kind of go through it for the first one, and then it's the same process for the others. So if we want a frequency of 100, we can put this on the 100, but then we need our frequency, continuous frequency dial turned around to the 1, we need a time here to get these maybe a little bit closer together. And then we need to decide how many spaces do we want. So our frequency is the period is 1 over the frequency. If the frequency is 100, then 1 over that is 0.01. And then in terms of milliseconds, that's 10 milliseconds. So I have this on 2 milliseconds per division. So 10 milliseconds is 5 divisions. So we have 1, 2, 3, 4, 5. So it's almost right. Now, to get it a little bit better, we can turn this knob, we can change this a little bit so that we get exactly 5 centimeters horizontally. Okay, then I have it where you can fill this out. So we have this on 2 milliseconds per centimeter. We need 5 divisions. Then we need to measure the voltage, and here it is 2 volts. Then we're going to use our meter. So we have our orange meter. Make sure you have the one that measures voltage. So I have the black in the common. I'm going to just sit it here. Oh, turn it on. And after I measure it, I'll hold it up where you can see it. Voltage, I've got it on 20. Make sure that you have it on the voltage. Oh, that's convenient. The voltage that has the little wiggly line. That's the AC voltage. So we know it's 2 volts. I'm going to put it on 20. Also make sure that you're looking at the end that has the little arrow on it, because if you use the other end, it doesn't work. So we have 20 there, and now I'm going to measure across the resistor. So I'll put that there and that there, and we get about 1.35.
Put your hand right above the display.
What?
It's flashing white. The meter.
The what?
The meter. There's a glare.
Oh. Adrian was telling me to tilt this a different way. Okay, because it was glaring on it where you couldn't see it, which is not very helpful. So we have about 1.35. That's a little bit different than I had, but it still shows that the RMS value that we have is not the same as the peak value. So then the last column is you're going to divide the meter voltage by the peak voltage, and then you're going to continue and do this for several different frequencies. Now, what I would recommend is you're going to do the same thing for all 3 waves. So while you have this set at 100 cycles per second, it's very convenient to go over here, change this to the triangular wave, and it looks like the amplitude stays the same. You can make the same measurements, and notice that the voltage here changed. It's not as much when we have the triangular wave as when we had the sine wave. And then we can go over to the square wave, and notice that we're actually a little over 2 volts. So while you have the frequency set, I would go ahead and make all the measurements for the 100 hertz for all 3 frequencies. And then you can go back and do the second row. You have 400 hertz. I would figure out the time and just kind of fill out that row, go through all 3 waves for the 400, and you might need to, on the triangular wave and the square wave, you might need to change the amplitude just a tiny bit to make sure that it actually is the 2 volts, the amplitude of 2 volts or 4 volts peak to peak. Okay. There is an explanation at the end of each of these sets of measurements about the RMS value. It tells you how that can be obtained. You don't really need to remember that. It tells you the value, so that's really all that you need. And I think that that actually takes care of this lab.